Hi, Mr. Richards here, and today's lesson is on recursive formulas. Our objectives are to use a recursive formula to list terms in a sequence, additionally to write recursive formulas for arithmetic and geometric sequences. But before we continue, we need to figure out what is a recursive formula. A recursive formula allows you to find the nth term of a sequence by performing operations to one or more of the preceding terms. And the best way to do this is to roll up our sleeves and find the first 5 terms of the sequence. Our first term, a1, equals -8, and then a of n equals -2 times a to the n minus 1 plus 5, as long as n is greater than or equal to 2. Now what this n minus 1 here is saying, if n is our current term, then n minus 1 is the term before that. So if we're looking at an being the 5th term, n minus 1 would be the 4th term. So our first term, a1, equals -8. Now how we find the second term? a2 is going to equal, we use this formula now, -2 times a to the 2 minus 1 term plus 5. Well, this 2 minus 1 term, -2 times a to the, is the first term. So we're basically then going to put our first term, which is -8, in for a1. So -2 times -8 plus 5. Well, -2 times -8 is 16, and plus 5, well, that's 21. So our second term is 21. Now, what about the third term? Well, this is going to equal -2 times a to the 3 minus 1 term plus 5, which is -2 times the second term plus 5. Well, the second term, as we calculated, was 21 plus 5. So that's -42 plus 5, which is -37. So our third term is -37. Now for the fourth term, well, -2 times a 4 minus 1 term plus 5. That's going to be -2 and the third term plus 5. And our third term was -37, so -2 times -37 plus 5. That is 74 plus 5, which is 79. So our fourth term is 79. Now lastly, the fifth term, we're going to take -2 times the fourth term plus 5, and our fourth term was 79. And -2 times 79 is -158, plus 5 is -153. So our fifth term is -153. So then, our final answer, we can write as -8 was our first term, 21 was our second term, then -37, 79, and lastly, -153. Another key concept in this lesson is writing recursive formulas. Our first step is going to be to determine if the sequence is arithmetic or geometric by finding if a common difference or a common ratio exists. If it's an arithmetic sequence and we have a common difference, we'll use this to start. If it's a geometric sequence, when we have a common ratio, we'll use this. And then we'll state the first term and domain for n. Now, 23, 29, 35, 41. Well, let's start by looking to see if there's a common difference. From 23 to 29, I'm adding 6. From 29 to 35, I'm adding 6. And from 35 to 41, I am adding 6. And so that we have a common difference of 6, which makes this an arithmetic sequence. Now, because of that, we're going to use this here. So we'll start just by writing a(n) equals a(n minus 1) plus d. So a(n) is going to equal a(n minus 1), and our common difference was 6. So when we finish this to write this in the correct notation, we need to use our first term and the domain. So we're going to say our first term, a(1), is going to equal 23, and then we can write a comma and write that sequence that we just came up with, a(n), or the formula we just came up with, a(n) equals a(n minus 1) plus 6, as long as n is greater than or equal to 2. So to recap, we found that there was a common difference of 6, made it arithmetic, so we use this recursive formula right there. And then to finish, we write our first term, the formula, and our domain, where n is greater than or equal to 2. Now, as these numbers in example 2b are bouncing back and forth between positive and negative and are, there is no common difference here. There has to be a common ratio. And so since we're looking for a common ratio, we can say, all right, let's look. Negative 21 over 7, 63 over negative 21, and negative 189 over 63. All of these simplify into negative 3. So we can say that there is a common ratio of negative 3 as we looked at our sequence. And since it's a common ratio, that means it's going to be a geometric sequence. And since we're at a geometric sequence, we're going to use this recursive formula. So we'll start. a(n) equals r times a(n minus 1. So a(n) is going to equal that common ratio, negative 3, times a(n minus 1. And to just clean that up, we do not even need the multiplication sign. We can just write negative 3a n minus 1. And now to state the first term and the domain, our first term was 7. So we're going to write this out as, okay, our first term a(1) was 7, comma, then the formula we just came up with, a(n) equals negative 3a n minus 1, comma, and our domain, we have to start with the second term. So n can be greater than or equal to 2. And that is that answer. So now we're going to take that information and try to write both recursive and explicit formulas. The price of a car depreciates at the end of each year, and we want to write a recursive and an explicit formula for the sequence. Okay. Well, as I look, the years I'm not really going to be concerned about, but what I am going to be concerned about are the prices. As I look down, it's not looking like a common difference, it's looking like a common ratio. It's looking like a geometric sequence. And so when I look at the difference between here, 7,200, and write this as a ratio, over 12,000, and I look at 4,320 over 7,200, and then lastly 2,592 over 4,320. When I divide, these all simplify into 0.6, which means I have a common ratio of 0.6, which makes this a geometric sequence. Now, once I know this is a geometric sequence, I can go back to the previous example and start with our formula a(n) equals r times a to the n minus 1. And our common ratio was 0.6 or 6/10. So a(n) is going to be 0.6 times a to the n minus 1. Now, to finish that off, let's write our first term. A1 is going to be 12,000, comma, our formula, a(n) equals 0.6 a(n minus 1. And that is our recursive formula for the sequence. Now, what about an explicit sequence? Well, here we can use the formula for the nth term of a geometric sequence, which, if you remember, was a(n) equals our first term a1 multiplied by our common ratio r to the n minus 1 power. So a(n) equals our first term a1, which was 12,000, times r, which is 0.6, to the n minus 1 power. So just to rewrite this here to show a little bit more room, a(n) is going to equal 12,000 multiplied by 0.6 to the n minus 1 power. And so now our last example is to translate between recursive and explicit formulas. For each recursive formula, write an explicit formula, and for each explicit formula, write a recursive formula. Well, this a(n) equals 2n minus 4 is a classic example of an explicit formula that is an arithmetic sequence. And here's what we can take out of this. We can say D, our common difference, is 2. And then we can solve for our first term, a1, because we need to solve for our first term, is going to be 2 times 1 minus 4. So my first term is 2 times 1 is 2, minus 4 is negative 2. And so now, to get this into a recursive formula, we're going to use our arithmetic sequence. So a(n) is going to equal a(n minus 1 plus d. So a(n) is going to equal a(n minus 1, and our common difference was 2, so plus 2. And now to finish this up, we need to write this with our first term. So a1 equals negative 2, comma, our formula, a(n) equals a(n minus 1 plus 2, as long as n is greater than or equal to 2. Now, we have an explicit formula here. Our first term is 84, and an equals 1.5a, then the n minus 1 below, plus 5 if n is greater than or equal to 2. Well, this is a recursive formula. That is a geometric sequence. And so there needs to be certain information that we pull out of here. Our first term is 84. Our common ratio is 1.5. So to write this now as an explicit formula, that is a geometric sequence, we're going to follow the pattern an is going to equal our first term, a1, multiplied by our common ratio, r, to the n minus 1 power. And so now we just need to make our substitution in. an is going to equal our first term, 84, multiplied by 1 5/10, or 1.5, to the n minus 1 power. And that is it for this lesson on recursive formulas, and it is also our last lesson in Chapter 7. Good luck.